This video will cover uncertainty and what we should be doing about it as GIS professionals. So first, note that all data has error or uncertainty. There's a quote, all models are wrong, but some are useful. I would say the same thing is true of data. All data is wrong, but some is useful. As an example, if you've got a 30-meter DEM, you wouldn't want to build a road from that, but you could use it to predict large landslides, and we do. So the data, the accuracy of the data, the precision of the data is going to be dictated by the problem you're trying to solve. So you need to get data that will allow you to solve that problem. Otherwise, you've got to get different data or change the problem. So that's really what you need to know, is what's required for the problem you're trying to solve. And I'll go through a bunch of things about uncertainty, why it's important, some definitions, some sources, estimating, reducing, and maintaining it, and especially reporting it. It is important to know the consequences of error. So if you put up a map, folks are not going to look at it and say, I wonder what accuracy that map is. They're going to assume that it's true. So we really have a responsibility to make sure that we are communicating the accuracy of our data, especially in something like a map. If you show a bar graph, you can put whisker plots on it to say, here's some representation of the uncertainty of this. Harder to do with a map, although there are some examples of it, and I'll show you one at the end. Okay, some definitions. I will talk about accuracy precision a little bit later. Gross errors are just that. They're big errors that are usually pretty easy to identify. But there's a whole bunch of other issues we need to look at: drift over time, gridding, collection bias, conversions, digits after the decimal, and the sources of uncertainty. We'll talk about all these things a little bit. First, note that whenever we look at spatial data, there is, of course, the spatial element to it. Typically, that's looked upon as coordinate uncertainty. So how good are our coordinates? We played with that with GPS start of the semester. Time is also important because the world changes and our data doesn't. So when the data was collected is important. Similarly, all of our attributes have uncertainty, and this you may have worked with before. If you're measuring diameter, breast height, there's going to be uncertainty of that. You should do the same tree several times, see how good those measurements are. What's their standard deviation? Relationships we haven't talked a lot about, but topological refers to the spatial relationship between features on the ground. We see this most commonly with boundaries, like maybe a boundary between a public forest and private land. The topological errors would be how well those two line up. They should line up perfectly, but of course that doesn't happen very often. Usually there's some issues there, and folks spend a lot of time working out those issues. There's a lot of sources of uncertainty. I don't think the real world really has uncertainty, or at least we're trying to represent the real world, so we'll leave it out. But everything else here that's marked in red is a potential source of error, and ones that I see error in on a regular basis. Excuse me. Measurements, of course, have error, as we've seen. You might be surprised to find that if you store your data in something like a database, you may not get back exactly what you put into it. And we'll talk a little bit about that. Processing and analysis, of course, introduce uncertainty into our data because it's changing it. And especially as we're going through our analysis, are we looking at that with a mind towards uncertainty and what it really represents instead of what we want it to represent? Once we publish our results, we need to make sure that we're careful in representing stuff and potentially representing the uncertainty as well, but not presenting it as being more accurate than it is. And no matter what we do, when we show our results to folks, they could misinterpret it. So we need to do our best to make sure they don't do that. For some examples of error, this has got to be one of the most spectacular ones, where in 1999, the U.S. Mistakenly bombed the Chinese embassy in Belgrade. They're going for a military target. Instead, they hit the Chinese embassy. That was not planned. It did not sit well with the Chinese and caused protests around the world. They didn't note that they'd successfully bombed 78 targets. So it didn't matter that they were under 2% accuracy. What mattered was they bombed the wrong building, and that was bad. And what was discovered was they used an intersection method. In other words, they assumed the streets were straight and intersected two streets to find the location they were going to bomb. And if you've been to old towns in Europe like Belgrade, you'll realize why that was a mistake, because they purposely made the streets curve and have sharp angles and things to help defend those cities during medieval times. So that was a mistake. It was a GIS process error. Okay, so to walk kind of through the process here, whenever we have inputs, you can look at the gross errors, precision, and accuracy of your data, estimate all three of them, and then for gross errors, we tend to remove them. We try to maintain the precision. We can't improve it usually, but we try to maintain our precision, like by keeping the right number of significant digits. And then with accuracy, in some cases, we can remove it or compensate for it. And then we want to report all of these in our final reports. The common gross errors I find are things like using the wrong datum, missing spatial reference system or wrong spatial reference system, and things just being really bad. Putting the wrong data in a field. I see things like initials in latitude fields really commonly for some reason, not so much in longitude fields. But anyway, just putting data in the wrong place. And then transcription errors by swapping Latin long, which is pretty easy to identify here in Northern California. But if you're somewhere where Latin long are closer in value, it's very difficult to identify. Or dropping a negative sign. If you drop the negative on longitude, you end up going from Arcata to Russia. So that's pretty easy to see. And most gross errors are pretty easy to see. So like polar bears. Here's data from GBIF on polar bears. And you can see that polar bears are here in the Indian Ocean, which is probably a mistake. And you might think that them having here in the US and across Europe is also a mistake. But actually, those are polar bears at the Denver Zoo. And this one's in New Mexico, and then they're moving across Europe as they show up in zoos. And you can actually look at the time frame of these points and see that they've increased. So are these errors? I would call these gross errors because I want points for polar bears in the field, especially to do habitat suitability modeling. But the zookeepers put in valid points where there were polar bears. So sometimes a gross error could just be different interpretation for what the data should be. All right, with gross errors, what you want to do is count how many you found and then try and predict how many you didn't find. In other words, if there were 10 false polar bear points that were here, that means that there's some level of error in this data as well, even though we can't see it. If you have a 10% error rate, you have a 10% error rate. So even where you can't see them, there's still going to be errors. So that's why that's important. Only remove them after estimating it so that you keep that estimate around. And then you want to make sure that you review that process looking for those errors. And then in your report, put in the gross errors that found and an estimate of the gross errors you think are still remaining in the data. Okay, two very important terms, accuracy and precision. So both of these talk about uncertainty, but of different types. If you are accurate, then you are on target. If you are precise, then you have high repeatability, okay? Or your data is clustered together. Now, this is pretty easy if you're into archery or some type of target practice where you're trying to get good at hitting the center of the bullseye. And here we're on target, here we're off target, but highly repeatable. So here we have high accuracy, low precision. Here we have high precision, low accuracy. Now, how do you improve your precision? Well, that's hard. You've got to get better equipment, get better at shooting, which means more training, better protocols, being more careful collecting data. Low accuracy, however, once you understand the accuracy, the nature of it, you can often shift your data over and up and improve the accuracy without having to recollect data. The key is understanding the accuracy. Quick example, these are some streets up in Corvallis that I found really interesting from two different data sets because, yeah, like what's going on? I've never seen two street layers look like this where not only were they shifted, but they're just kind of different. And one may have been taken as an old data set and one is newer with better equipment. The green has straighter lines, so I'm guessing that might be newer, but hard to tell. Maybe one was taken off remote sensing and they were taken at different resolutions. So if we hadn't put these two together, we wouldn't know there was uncertainty, right? So that's one of the dangers. And notice there's also lines on the red one that don't show up at all on the green. So this is one where I would definitely get out in the field and find out what's going on. But again, if we hadn't had two data sets, we wouldn't have suspected there was this level of error. Okay, so accuracy is also known as bias or the distance from truth. So if here's our data set and we found an average mean, the bias would be the distance from truth. Now, of course, the issue with accuracy and bias is being able to find out what truth is. Again, we did this exercise with our GPS where we had a higher source of truth, and you need that to be able to estimate accuracy and bias. And these two terms are used pretty much interchangeably. Accuracy tends to be used more to talk generally about bias, and bias is more specifically this distance between your mean of your data and truth. As an example, here's some data on tamarisk from the institute that I used to work with in Colorado. And if you take a look, you can see that the data tends to be near roads. We found this over and over again. In the case of tamarisk, it's also around lakes. Well, sure, because roads are easier to get to and lakes are easy to walk around. So that's where folks are finding tamarisk. That didn't mean that it wasn't out here in the middle of nowhere. It just meant that's where we were sampling. So there was a bias towards roads in our sample data. Good thing to watch out for. Our solution was to send folks off into the desert. And sure enough, they found tamarisk out here. And so we corrected some of our data that way. Now, in order to estimate the amount of accuracy, again, you have to have ground truth data. That's the hard part. You've got to make sure you got really good data. And then you can use RMSE, root mean squared error, to estimate your accuracy. Compensating for it is difficult. You may need to re-georeference your data if that's the case, if there's a shift like between NAD 27 and now at NAD 83. If there's lots of points, sometimes you can look at the data and see that it's shifted, and then you can adjust compute accuracy and adjust it based on that. I'll talk a little bit in a second about dates. Okay, so RMSE. So RMSE is very closely related to standard deviation, except we've replaced the mean of the data with our truth. So we've got the difference between all our samples and truth. We square that to get rid of the negative, sum them and divide by n. Now we've got an average squared difference. Then we take the square root. So this gives us root mean squared error, basically an average of the error that we're getting. Because of the square, it's not quite an average, but pretty close to an average error that we're getting. Okay. All right, precision. So precision is different from accuracy. We can estimate it using standard deviation. Standard error is usually used to estimate the precision of means, sample means, when you have multiple sample data sets. Confidence intervals we can use, min-max, I'll talk about those. And then to manage it, we want to make sure we maintain our significant digits. Oh, and watch your data types, right? Because if you convert doubles to longs, you just lose anything after the decimal. And then make sure to report it. All right, most important curve in precision is standard deviation, or sorry, normal or Gaussian curve, and the measure of its width, which is standard deviation. So here we go. So one standard deviation, okay, on either side of the mean is going to contain about 68% of our data, okay? Or a lot of folks remember it by saying 2/3. In other words, 2/3 of our data will be within one standard deviation of our mean. Now, this is if our data is distributed using a normal curve or Gaussian curve. Most natural resource data has that characteristic or approximate that characteristic, which means we can do it. Okay, and then 2 standard deviations, we're going to get 96% of our data, and 3, we've got over 99% of our data. So it drops off very quickly, but remember, it also means that there could be points out here in the extremes, and that's really important. Confidence intervals are similar to standard deviation, except they're usually around a distribution. And that means that your confidence interval represents the 95% chance that if you collect data and build a model again, you're going to get the same thing. And we'll talk about that in 570 if you take 570. Min-max is the one to be really careful with, and I do see this used regularly. And what tends to happen is folks say, oh, look, all of our data is between this value and this value. They state that as a min-max, and then another data point pops up in the future that's off outside of that. It only really works if you're representing data that has a fixed boundary, like the height of a tree is never going to go past, is going to go negative. So you could say 0 is the minimum, but what's the maximum, right? And if you say a tree is 150 feet tall maximum, well, then you turn around and find what's 151. So standard deviation tends to be a better approach for most data. Another one that's interesting with precision is if you take a date, just a year, like 2011, and you put that into a relational database like Microsoft Access, SQL Server that I use, what will come back to you is 2011, January 1st, midnight. In other words, you lose the precision that's associated with the fact that you only have a year. And we've seen this pop up in studies where we needed to know the month and the day that the data was collected, especially for phonology studies or for migration studies. So we had to associate with the data how precise was it. In other words, if we had a year, we had to say this is just a year. Don't assume that this data is resolvable to a date, to a specific day in a month. Okay, so that's again important to have that documentation with it. All right, so examples of how to manage this. By far the most important thing, especially with field data, is having a protocol. These should be specific step-by-step instructions on how to collect data, including calibration of people and equipment, the equipment and training that's required. They should be step-by-step and include QA/QC. The GLOBE project is an international project to monitor weather, and they have some of the best protocols I've ever seen if you need examples. Okay, so as an example of how this can go wrong, this is some Oregon fire data that a student up at Oregon State brought me. And the student planned to make a 1 kilometer model with this data and hadn't really brought it up into a GIS package and zoomed around and looked at it, which definitely you want to do, because very quickly, in just a few minutes, I was able to find that, oh yeah, the data looks good over here, but over here it looks like it's gridded. Sure enough, it was gridded, and these are 4 kilometer grids. In other words, someone took this data, probably converted it to a raster, and then converted it back to points, thus losing precision of this data. Okay? Now you really lose both, right? You lose precision, and then you lose some accuracy. It's not on target. It's not repeatable. It's just messed up. If you want to work at 1 kilometer, if you want to look at 4, you're fine. And that's what they ended up doing. This is called quantization or gridding. Happens with fire data as well as other types of data. Best you can do is estimate the amount of it using a minimum distance algorithm and then create a histogram. Can't really remove it that I know of. It's there, and you definitely want to report it. Another one that's a big source of error that I don't see documented very often is interpolated surfaces. A lot of the surfaces we use, especially rasters that we use, certainly for weather, temperature, precipitation, they're created usually using kriging or another interpolation method. And kriging does give an estimate of error, but the other methods don't. Escalante National Monument is the largest national monument in the US. There are 3 weather stations in it, but you can get 1 kilometer weather data. The weather stations are like 100 kilometers apart. So there's quite a bit of error there. You can use cross-validation and with other methods to get an overall root mean squared error, and often folks end up with pretty high errors. Doesn't mean you can't use the data, but at least we know what the error is within the data so we can decide if it's appropriate to use. Again, we'll talk more about that in modeling. Okay, Horsetooth Lake. So here's another thing to remember is when we talk about things like the area of a lake. Well, are we talking about when it's full or when it's empty? Usually it's when it's full, but we need to be explicit about that. And reservoirs are rarely at their full height. So if you're looking for something like the average volume that's in a reservoir, it wouldn't be at the full height. So things to consider when we're looking at data temporally. All right, most important thing for you for this class is remember to document the uncertainty associated with your data. Record the accuracy and precision in your metadata so other folks know it's there. In any of your outputs, record the data sources, sampling procedures, processing methods, and estimated uncertainty. Most of this would, of course, be captured in your methods and your reports. To deal with things like estimated uncertainty and any other issues that you have, like usually we don't know exactly what the error is, what we did is we just started adding caveat sections to manuscripts and found that works pretty well. In other words, just add a section to your manuscript that says, here's other issues that might be appearing that we weren't able to nail down as well as we'd like. And last note on this is just remember to keep your significant digits. I recommend keeping them through the processing. Don't worry about how many you have. And then when you do your final report, make sure you reduce them down. And usually we reduce them down pretty far, which is fine because then you're not over-representing the accuracy of your data, accuracy or precision. Again, for your documentation, please include information on gross errors, accuracy, and precision. We would love to be able to create maps that show uncertainty, but there are very few results of these, and it's hard to do. This is some data on shipping lanes, a model of shipping lane uncertainty that was done by a student, Colleen Sullivan, up at Oregon State, where she looked at the shipping lanes and how accurate they were being portrayed. And you can see here near the coast, you might assume that you could work around the shipping lanes, and part of the work being done up there was for MPAs, marine protected areas. But you can see with the uncertainty involved, you'd pretty much want to avoid the entire coastline, and these larger areas out here would be safer to work in for research especially. Thank you much.